just to mention, I did the inequality the wrong way here, so make sure you change that in your notes. I was just trying to prevent this thing from going negative, but I did it the wrong way around. There was also a question about the conditional rate distortion function. If we know y, so maybe I say a quick word about that. So suppose yn is known by the encoder also. Then it turns out the rate distortion function is given by, I think in the course notes, it's written like this. It's the min over all px hat given x. So you'll see there's no auxiliary random variable needed, and because of that we don't need a function, because we're generating this directly. So this is the problem. And it turns out the answer is given by just the average rate distortion function, right? If I have this, then I'd have rate distortion function. This would be the rate distortion function, but with y you just add that, which is just an averaging over y. So it's like what I said, you collect the, one way of proving that this is achievable is just collect all the positions y where you have zeros, and then you can get ixx hat given y equals 0, obviously, and then same for all the others, and just average, and that's the achievability. Now if we talk about Gaussian channel, let's think of the Gaussian case, and let's just prove that this is the rate distortion function for that case. It's not very hard, because if I start with this, I'll just go through the same steps we did for the Gaussian rate distortion function. The only thing that's new is the y, right? So here we'll get x hat and y, right? Now this thing here is equal to h of x minus x hat, obviously, so I can just subtract that off. And then I can say, oh, but that's less than h of x minus x hat, right? And since this thing here is going to be less than 1/2 log 2 pi e by the maximum entropy theorem of the expected value of, I should say, the variance. But of course, you know, you can make it 0 mean, right? And I know that this has to be less than or equal to d, right? So this whole thing has to be bigger than h of x given y minus 1/2 log 2 pi e d, and I'm done. Right? Because again, this thing here is just what's on top, right? And so there's your lower bound, and so that I don't have to do any more work, since I showed for without knowing y at the transmitter I can achieve this, and I know that's the best I can do, then I'm done, right? So that's the remarkable fact. It's that you don't, to get that rate, we don't even need y at the encoder. Again, it doesn't mean that isn't useful, because, I mean, it's much easier to design a source code for this problem because we don't have to do any channel decoding at all, right? So it's just a pure compression problem, which we have here already. And you don't have to do any hashing, or so we don't need this piece, and we don't need the sophisticated decoder. So definitely you do simplify the problem by getting yn at the encoder. Okay, so that's just to complete that part. So one thing I do want to do yet here is the converse. I should be able to finish also the Gelfand-Pinsker problem, because there we'll move faster. We'll just, you know, since we're now used to what compression and decoding does, we'll see the same steps appear, and we'll argue a little bit faster about what the rates are. So, I mean, once you get used to these things, you can do, once you get used to this, you can effectively, in a few minutes, derive all the achievable regions in the literature, effectively, because all achievable regions in the literature are just based on these simple tools. There's one more thing we do have to introduce for the broadcast channel, but you'll see it's nothing so dramatically different. This is also one of the kind of disappointing aspects of network information theory. There are certain basic tools, and they give you the best rates, and we don't know what more to do, right? Well, there were a few. There's one. Well, we have to do superposition coding. We have to do Martin coding. We'll talk about those. There was one new invention, that's the compute and forward work by Nazir Gaspar, which is really based on Kerner Martin's, approach. Also, it's the same as lattice coding, so they've made their various authors associated with it. And beyond that, we don't really have a lot, right? So it's kind of unfortunate, disappointing. Some people get unhappy about this. I don't know, maybe. Fine, so let's talk about the converse now. So I'll leave that rate on the board, I think, because we'd later like to contrast it with the Gelfand-Pinsker problem. So let's do the converse theorem. This one's kind of nice. I mean, it turns out it has a very nice form, and we'll kind of get the result quite quickly that we want. So we again start with the same bound, that the entropy of W has to be less than NR, or the number of bits we have, certainly by the data compression theorem, has to be bigger than the entropy of W. That's just the classic data compression result. And then this is, of course, bigger than something that looks like this. Okay, why is that? Well, I can write this as the entropy of W given Yn, which is less than that, minus the entropy of W given Y and Xn, which is non-negative, right? So that one is easy to check, right? So whenever you convert a random variable into mutual information, you just make things smaller. Okay, but do you see it, everyone? Well, I mean, I could write it out separately. Let's do it this way. This is bigger than this, and of course that's bigger than this. Because then I'm just making it smaller, and so the whole thing just becomes I of Xn. W given Yn. And you already see it has a similar shape to what we had. Remember, this quantity here had the form I x u given y. Right? This difference is the same as this, so that's what we're trying to mimic in a way. Okay, so let's write this out. This is h of y and xn given yn minus h of xn given wyn. And now let's say this is just add out use the chain rule. This is h of xi yi, of course, because these are memoryless sequences. And here we'll use the chain rule too, h of xi given w. And let me do the following. Well, let me write it all out. Y and xi minus 1. Right? Now I can write this is less than or equal to. Let me drop this so I get just something bigger. And let me reorganize. Let me take out the ith term here, and then take all the past here, all the future, and all the w, and put it together. Okay, and this is what I will define to be my ui. I'm just thinking about now whether I had to drop that past one. Maybe I didn't. Not that it really matters. But I guess I could even drop more of these. I have to think about that for a moment, whether that's necessarily the only choice. For some reason I think it is, but I don't remember why. Anyway, this here is bigger than well, now we just have h of xi given y minus h of xi yi given ui. So that's just I of xi ui given yi. And what we should, okay, so now I'd like to bound this. And if we look at this RWZD, well, this is the smallest. This here is the same as IXU given. So I could write this here as IXUY. So the smallest possible value I could get here is given by the Wiener-Ziev rate distortion function, as long as we have this Markov chain, right? Because the Wiener-Ziev function has the Markov chain condition in it. So we have to check whether we have that Markov chain here. Do we have the Markov chain here, ui, xi, yi, with this choice of ui? That's the main question. If we do, then I can upper bound this by the Wiener's rate distortion function with, the corresponding expectations plugged in. Well, we'd have to check this. Let's see here, the I. You see that W, so W is in here. Let's see here, W is in here. Well, I guess this, like, that's fine, because yi is just a noisy function of xi. And I guess I could have kept the past xi minus 1 in here too. So I don't see right now why I couldn't have kept this in here, why I had to drop it. It looks almost to me like I could keep it. Not sure why I wrote it now necessarily in this form, because I would still have the Markov chain. That's all I need to apply the bound, actually, right? So I don't see a reason for it right now. Maybe there is a reason. Oh, no, there is a reason. Because I also need to have x hat to be a function of f, u, and y, right? And if you look here, what is x hat a function of? Well, if we look in this, we have to look at it, we're doing the converse, so we have to look at the full picture. Well, this is some function of all of w, what I see in all of yn, right? But that's the same as a function of ui and yi. You see that? Because if I include yi in here, I have all of y and all of w. That's why I can't take the xi minus 1 inside. Well, I guess I could, because then it would still be a function. But I can't drop, I certainly can't drop these 3. But I think if I included the xi in here, then it would still be a function of it. So I think I could, like, what it seems to me, the reason I dropped this because it is the nicest form, right? But I don't think I needed to drop it, because I would still have the Markov chain and the function, and that's all I need. Like, I need to satisfy everything that's in here, right? So it seems to me that I could have done that. I don't see a reason now why I have to drop the xi minus 1. I'll have to think about that a little bit more. But certainly if I drop it, everything's fine, right? Then it matches 1-to-1, right? Matches 1-to-1. So since I have that, and I've checked that now, so for all I this is true, then I can right away say, aha, but this is bigger than the minimum possible such value given all those constraints. So this is bigger than our Wiener-Ziv of the distortion at that point. So d of xi f of ui yi. Because the Wiener-Ziv rate distortion function gives me the minimum possible value. If that's the, if I measure this, value here, then and plug that into my d, then this gives you the minimum mutual information of that shape, right? So I'm adjusting the distortion to match that, what I want. So this might just be the suboptimal distribution for that distortion, but at least it's bigger than. Now, there's one thing I need, which I didn't mention. I do need a property, which we're not going to prove, of this function. And that turns out to be interesting. It's not so obvious how to prove this, but it turns out this is convex in P u given S if f of d is if f is fixed. And that's proved in the course notes. I should have it here somewhere. Convex in D, sorry. And the way you prove it is that you prove a convexity property of this difference, of course. Right, but it turns out this is convex in D, and because it's convex, I can write this as, multiply by n, divide by n. We'll get this. That's what I'm looking for. And now I'm basically done because this is the distortion, and I know that this one has to be less than or equal to D. So this is bigger than or equal to NRWZD because I have another property, and that is obviously that this is decreasing, non-increasing with D. All right, that's what I used here. The non-increasing property here, I used convexity. Convexity, non-increasing. Okay, that's the converse. So again, what's important in the converse is that I keep at least these. And I have to check, but it seems to me almost, I don't see a reason why we had to drop the xi, but we may as well, so it doesn't really matter which way we go. Questions? So that one comes out kind of nicely. There weren't any special tricks needed to do that. Okay. Fine, so with that, we can move to the dirty paper coding problem. If you're fine with it, that's the dual of this problem. So that's not immediately obvious when I write out the problem because it looks quite different, but you'll see that the structure is basically the same in terms of the encoding and decoding once we derive that. So let's talk about the popularly known as dirty paper coding problem. I like to call it Gelfand-Pinsker problem because as far as I know, the solution was originally first given by two Russian researchers, although I think, you know, Abbas El-Gamal did some work at around the same time, so I think there's some, people have a little bit of different opinions who came up with what first, but I think Gelfand-Pinsker, it was N70s, and I think Abbas's work was a little later. There was also some parallel work by some other people like Tsibakov and so on, but I think it was a little less general as far as I know as what Gelfand-Pinsker did. So let me just call it the Gelfand-Pinsker problem. So, I mean, I don't know if I ever met Gelfand, but Pinsker I had the fortune to meet a few times. Once in Zurich, he came together with some researchers. He was already an older man, and once as PhD students, there were a bunch of us that had the chance to visit Moscow, IPI in Moscow, and he was there too. It was a lot of fun experience. You get to know the Russian culture, which is very different than what I'm experiencing here. Russians like to, really discuss stuff out, right? I mean, they at least at IPI they did. So that when everyone who gives a talk, if you ever have a chance to give a talk at IPI, you'll find that the typical thing is you stand up, give a talk, you say a few sentences, and then they say stop, and then they discuss in Russian amongst each other. You have no idea what they're discussing. And then maybe after 5 minutes, the person who said stop says, "Okay, keep going." Then you go another 5 minutes and stop, and then the Russians, and so you really get maybe 10% of your talk done. I'm not making this up. This is really the way it is. That's what I experienced. I've heard other people say the same thing. But it tells you they're very interested in the problem, right? So okay, so here's the problem. We're now going away from source coding back to channel coding, but anyway, we've already seen that source and channel coding are closely related with the Slepian-Wolf problem, right? So, but anyway, now we have a message source. So this is a certain number of bits that we would like to communicate reliably to a receiver. We have an encoder. And we have a channel. You've seen this all before. Py given x. We have a decoder, and we have the sync. And the goal is to make the error probably small. Now, what's new in this problem is that you have something people, in information theory love, this thing called state, channel with state. I think this comes from Shannon's terminology. So what we have is another random process that enters the picture. Now, what is this random? What does that mean? Well, you can think of it as being interference. So, for example, one model we will study here is this model, x plus s plus z, where z is a Gaussian random variable and x and s are real numbers. And this is called like the dirty paper coding problem, but it's a special case of the more general result. It could be something else. It could be a fading, right? It could be, you know, s times x plus z, right? Then you would have a fast fading problem. But the point is, it could be interference, it could be fading, but there's an additional random process happening in the channel. Now, without anything more, this would just be a new channel py given x, which is averaged over s. But what's going to be new here is that for some weird reason, which I think if you see this the first time, you think, why in the world would this ever make any practical sense? This state is known at the encoder, but not at the decoder. Right, now, if it was known at the decoder, then it turns out the problem will be much easier to solve. And if it's known at both, it's also easier to solve, just like we saw for the source coding problem. But where it's really a little weird, and where it will be interesting, is if the channel state is known like at the encoder. And you already start to see maybe a little bit the Wiener-Ziv problem, where something extra information was known only at the receiver. Now it's only known at the encoder, but we have a channel coding problem rather than a source coding problem. Okay, so the problem here is the same as before. So this is non-causal. So this is also important. So Shannon looked at the case in a 1959, I think, paper where this here was causal information or strictly causal. So causal means I have the current state available at the time I'm transmitting my next symbol, or strictly causal means I only have the past states available. So Shannon looked at the case where you have causal, where you know the state at the time you're transmitting, and then the theory changes again a little bit. So here, the interesting thing is you have the whole state sequence ahead of time. Okay. So the problem, as before, is try to find an encoder, you know, find the maximum R, find the maximum rate, such that for sufficiently large n, there is one A encoder-decoder pair such that the error probability PE, which is the probability that the output is not equal to the input, is as close to 0 as desired, other than 0, right? We don't require 0 error probability. Okay, so that's the problem that we have. Now, what are some applications? Well, the non-causality at first glance makes everything completely ridiculous. However, there are some problems where this fits. So, for example, and this is also where the word writing on dirty paper comes from, you can think of having like a piece of paper. I give you this piece of paper here. There's writing on it, so you can't quite fill it as much as you could before, right? So what can I do now, given I know this at the encoding side, but the receiver doesn't know what the writing was at the receiver side, just as an example. Okay, so you can think, so in fact, Sibikov, and I don't know if it was Sibikov alone, he also looked at this problem, but from the perspective of writing things into memory that was already, which has some stuck cells. So you can think of also a CD where you've already printed something on. So you can print something else on it, but you're kind of only can print on some of the values that are high in the first place, because you can't change the ones that have been depressed already. You can't pull them up, right? And you can read the disk before you write. Then you would know the state non-causally, and the receiver may not know it. So if you're reusing CDs, I don't know why you'd ever do this, but if you're using them, then this could be interesting. More importantly, this channel will show up when we talk about broadcast channels. So what happens in a broadcast channel? If you have a base station, there's some here somewhere, outside probably, I don't know, not in this room, I don't see any. But you have multiple receivers, say 2 receivers. Then there's a message maybe for one receiver, another message for the other, and the transmitter knows ahead of time what both messages are. So what you can do is first generate a code word for one receiver. The transmitter knows what that code word is ahead of time, right? And then can encode the next one by writing onto that, code word to adjust the next code word to fit. And that's where this setup becomes I think has the greatest applications, at least in terms of economical potential. Okay? And I'm convinced the codes that we'll talk about here will one day really become important in some chip and application, because it does help, even in terms of rate. And for this reason, I think it will be used. It's not used today at all, as far as I know, in any wireless base stations, but I'm convinced it will be in the future. I don't know how long that will take, because as we'll see, it's a little more complex to build this stuff. Okay, so let's talk again about the coding. So now we're accustomed to how we do our codes, and so I'll walk through it a little bit faster. But first, let's choose something. First thing we'll choose is an auxiliary random variable. So we're going to do a code book just like we did for the Wiener-Ziv problem. So we'll choose an auxiliary random variable. So we're going to create a u here. And then, of course, we'll choose a function, which maps u cross s, the set from this set u and so this should have been s, my apologies, s, to x, right? So what we're going to do is generate a code book of u's. We'll relate those to the interference or state, and then we'll map the state value and the u value to the x. So you can already again see the dual nature, right, of what I'm doing as compared to Wiener-Ziv problem, where we also had a u, but it was a u given x rather than u given s. And we also had a function. Now here we don't have a distortion. I could have added a cost constraint on x, then the duality will become even more apparent. But right now it turns out this problem won't have any kind of constrained optimization. We'll just do an optimization. You'll see. Okay, we'll get there. But the answer will look very similar. Okay, now we do our code construction. Okay, we'll generate 2 to the n r plus r primed sequences un, w, v, where w runs from 1 to 2 to the nr. So this is exactly the same construction, random coding construction, as the Wiener-Ziv problem, which again shows that source and channel coding is closely related. Exactly the same. Exactly the same. So let me draw it, though, just again to help visualize what's going to happen in a moment. So this is un11, un1, comma 2 to the n r primed. So here's our first bin, w equals 1, and so on. 2 to the n r, 2 to the n r prime. Okay, we'll just look at the first one, just to keep things simple. Okay. So that's our code construction using PU. Okay, so I won't just be more descriptive. It's exactly the same construction. Choose every letter of every code word statistically independently with PU. Okay, what do we do next? Encoder. Well, what's the encoder do? Well, it's given two things, right? There's two inputs, the message and the state. What does it do? Well, suppose the message is 1. So this is the subset we're interested in. And what will we do? We'll try to find a u that's jointly typical with respect to the state. So if you think of it this perspective, we're kind of aligning u with the interference. And if we're thinking of a channel like x plus s plus z, maybe that makes a little bit sense. We're kind of like we're riding on the wave of the interference. Like if S was really strong, we're kind of aligning things with S, and maybe that'll help us beat the noise. You can think of it that way. It's not a good intuition, but I give it to you anyway. Because we'll see in a moment that something weird happens for Gaussian channels. Actually, we choose what we transmit into the channel to be independent of the S, which goes kind of in the opposite intuition. You kind of go, what does that mean? So we'll see that happen. But we should discuss that, what that means. it's not so easy, I think, to get an intuition on some of these things. That makes sense. So given W and S, try to find V so that, so let me make it colored just to see what we're looking for, so that U and W comma V Sn is jointly typical, are appropriately aligned, U, S, U, and S. Okay? And of course, I have to make the size of the subset big enough so that happens. How big do I have to make it? Well, this is just a classic quantization problem. So interestingly enough, the first thing I do here is vector quantization. Weird, right? The first step of a channel coding problem is to do a vector quantization. Anyway, so what do I need? I need to have that R primed is bigger than IUS, right? That's what I need for my vector quantizer. All right, the code book has to be at least that big so that I find at least one. So I'm guaranteed to find one or more jointly typical pairs. Okay. All right, so I've done that now. Let's keep going. Now we've generated our U so that we're not completed with the encoding, right? So now given UN, W, comma, V, and YN, generate XI equals F of UI, YI, all I, and that's what we transmit. That's what we send over the channel. Okay? So we still have, again, we have two things to design, right? So these two things. So let me emphasize those. US is to design, and F. And everything I'm developing now is valid for any choice of these two. Okay? And then afterwards we'll optimize those when we look at some examples. Okay, we transmit over the channel. What does the receiver do? Well, the decoder will be, of course, a decoding operation now. Given yn, what can it do? Well, the receiver doesn't know where I am in this code book, so effectively it's kind of forced to decode both W and V, even though it doesn't care about V. Now you could think about this. Maybe there's a way of decoding W and V without decoding V. It turns out you can look at maximum likelihood decoders that do that, but you'll find that the rates are the same as if you decoded both, so we'll just decode both. All right, so try to find a pair, W hat, V hat, so that UN, let me do it colored, that's what we're looking for. W hat, V hat, YN is jointly typical with respect to PUY. Okay, and okay, so now in order to make that work, we have to make sure the code book isn't too big, and we also have to make sure that U and Y are jointly typical. So we're going to have to apply like a Markov lemma that says that since U and S are typical and S and Y are typical, and well, X, S, and Y are typical through the channel, then there's a Markov chain from U to X, S to Y, and so everything's fine. So let me write that out. But the Markov lemma appears here too, of course. So Markov lemma for the chain U, X, S, Y, right? So that's a Markov chain. And since the encoding step, what it does is it makes these two typical, and the channel makes these two typical, so the whole thing is typical because we have the Markov chain. That's it. So this is the encoder, makes these typical, and the channel automatically, well, with high probability, has those typical, and so U and Y will be typical, or the whole triple will be typical, and so then that lets us say our decoding error event, again, is a union bound, so what we'll need is r plus r primed has to be less than I of uy, right? The code book has to be at most this size. So you see we're losing rate because we've enlarged our code book artificially, and the purpose of enlarging the code book artificially is to coordinate the transmission with the state, and hopefully we gain more through that coordination than by enlarging the code book size. So there's a trade-off, right? And we're trying to find the best trade-off. Okay, and effectively that's it. If all this works, we've communicated reliably. So putting this all together, and here we don't have a cost constraint, otherwise I'd have to worry about averaging again, but putting it all together, we get the following achievable rate region. Let me write it down here. R Gelfand-Pinsker without a cost constraint is equal to the max. And now we can maximize over PU given S and the function f, and no constrained optimization of I ui minus the price we pay for coordinating transmissions us. Okay, and you see the I should also add uxsy Markov. I need to add that. But you see the duality. The only thing that's missing, this is a constrained optimization, but I would get that too if I had a cost constraint on the inputs and outputs. I would also get such that the expected value of the cost of the inputs and outputs are less than the cost constraint, like the power constraint. But it would be, then the analogy would be even better. Okay, so this is the Gelfand-Pinsker rate. It turns out to be optimal. We'll prove that, so we'll prove the converse yet. I think the best thing to do, though, first is to do a little bit of discussion and do the Gaussian example, and then we'll do the converse yet. And that's really all I had planned for today anyway, so I think we'll finish in time, actually. Okay, any questions about this? Okay, again, architecture, vector quantizer followed by a function, and here just normal decoding. So there's no hashing here, but vector quantizer is function operation. Okay, so let's do a couple of comments on this. Just like for Wiener-Ziv problem, well, we have a cardinality issue again. Cardinality constraint, same as for Wiener-Ziv. Theodori plus. What I mean by plus is enhanced Cartesian Eggleston strengthening of the Carathéodory's theorem. Carathéodory was more general, has to do with points and dimensionality, and as if the points that you're considering are connected, then there's a strengthening. That's why it's called the Carathéodory Eggleston strengthening of Carthéodory, but it's not really a strengthening. It's a strengthening under certain conditions for the set that you're considering, so then you can get a stronger result. So it's not really a generalization as such. I think it's the same. Now I didn't write it down, so let me look it up. I'll use my cheat sheet. Let's see here. I think it's u plus x plus 1, or s plus 1 or something like this. Paying attention to this is really only important once you're doing numerical optimization, and you can only do that for very small alphabets anyway. As soon as you get to things like Gaussian, you can forget all this cardinality stuff anyway, or even larger alphabet sizes. That's why I usually don't pay quite as much attention to this as I should. X times s plus 1. So let me explain why I say this is, bad. Like suppose this was binary and this was binary. Suppose this was a binary. That's the smallest interesting case. You're already getting 5. Now, optimizing over a 5-dimensional random variable with 5 values is not easy because you already have 4 probabilities to worry about. So you have a 4-dimensional search. Now it's only in the box, but actually doing that here isn't easy already for 5. Even for 5, doing that numerical optimization isn't easy. once you get to even a little bit larger in state or x, you can just forget it. You need to use analytic tools to work with this. You can't numerically optimize this anymore. So that's why, although the cardinality things are important, especially for converses, to sort of satisfy that you have something formally good in some kind of way, practically it doesn't really help a lot. To just, you need something even better than just cardinality constraints. That's my main point. I emphasize that a little bit because some papers emphasize that. They say if you come up with a converse without cardinality constraints, it isn't really a converse, but I would disagree with that for this reason, right? Because practically it's not really that important in most cases. In some cases it is, in some cases it is not. A lot of these arguments are a little bit philosophical, more than deep, I think. But anyway, it's just an opinion. Okay, some other things. We just like for the Wiener-Ziv problem, we'd like to see if we can make another form for this. Remember there we had, you know, something like xu given y. Can we do something like that here? And it turns out the answer is not really, because it turns out that the Markov conditions are slightly different, which is interesting, because so it's not kind of a perfect dual. So we get this, of course, right? So by writing this out as h of u minus h of u given y minus h of u, the h of u's cancel, minus h of u given s, but the negative negative puts it plus, we get that. But now we only have this Markov chain, right? And there's no x in here, so we can't yet, you know, plug in anything yet. However, what I can do is get a bound. So if I plug in s into here, this here is bigger than u given y s. And now at least I get I of u y given s. And now, again, s and u give me x. So this here is equal to ix. You know, I can put the x here, and then I can say, well, because x goes directly into the channel, this is actually equal to I of x y given s. And because you have the, you know, I can write this here as I x y given x plus I u x y given x, but then I have the Markov chain to say that's 0. Now, why is that important to me to write? Because if you look at this expression, you'll see s is in the conditioning, and that's what the capacity is if s was also available to the receiver. Okay? And s being available to receiver, of course, is very useful because then you can get rid of the interference. Like if you had this channel, you could just subtract off the s, right? And the problem is really simple. If it was fading, you would at least know what the fading variable is, but so does the transmitter, so you could do a water filling over time. Okay, this, you know, so if this sx plus e, you would get, of course, time water filling because you know what the values are. And so on, right? But this just shows, at least gives us consistency. It shows that the rate that we're getting is in general smaller than with knowledge of both. Would that better happen? We better get that. And what's going to be interesting for us are cases where we get equality, and of course the Gaussian case is the interesting one that will give us equality, at least the additive interference problem. Yes? Oh, yeah. Sure, sure. So here, in this problem here, in our coding, x was a function of s and u, right? You'll remember we had f, and so I can plug in the x here, and then the rest is easy, right? It's just the Markov chain. This is because, you know, yeah, so x is f of u comma s, right? Sorry? Oh, I could do that too. That's true. Yeah, so I could do that. But it turns out to be with equality. But I could do that too. That's true. Thank you. Even if it wasn't a function, it would still be true. You know, because we have the Markov condition. But okay, that's true. Thank you. So that would correspond to randomized coding or not, right? So, which we don't need here. Right. Sibby and I were talking about randomized encoding over lunch, so that's why. Yeah. Any other questions, marks? Okay, so there's two more things on the program, Gaussian channel and then converse. Both come with a little bit of interesting things. Turns out the converse is a little trickier here. Unless you know what telescoping is, then it becomes really easy. But anyway, it's a little bit different slightly than for the Wiener-Zip problem, which again makes it all the more remarkable that you have the duality. It's not, or at least in the expression, it's not that obvious, I think. So, fine. So, let's do this. So let's look at the Gaussian case, which got a lot of attention in around the year 2000 and 2001. I think it was really Shlomo who noticed this fact, because Giuseppe Cayer and Shlomo wrote probably the first paper to really point out the importance of Costa's dirty paper coding results, and then they won a paper award for that work. So let's look at this problem. Suppose this is the channel where this is their independent S and Z are statistically independent. This here is Gaussian noise with zero mean, and let's just say variance n. This here is any random variable with finite variance. Okay, so it could even be, in fact, you could extend this result that, like in this example, I'm assuming S is independent identically distributed. It turns out all these results, what I'm about to develop for the Gaussian channel, will also be true for any statistics on Sn. So it could be any, writing on the dirty paper. As long as there's Gaussian noise, I'll be able to do something interesting with this. Okay? So it's any random variable. So it's a broader result. So Costa proved this first for S being Gaussian, but it doesn't have to be. So the proofs go through even with that. Okay, so let's, what we have to do, let's try to do an achievable rate. So we need to choose a channel and a function. Of course, as usual, we want everything to stay Gaussian, so probably this channel should be Gaussian, and F should be linear. Okay, same idea as before. So what we'll do is do the following. We'll choose U to be the following S plus noise. It's going to be slightly different than you might expect. It's not S plus noise. It's going to be alpha S plus noise. And the noise is going to be the X. Okay, it's a valid distribution, right? It's just a and this also gives us our function right away, right? Because X is U minus alpha S, right? So we get both in one shot. We're getting the channel from S to U, which is alpha S plus X, and that immediately gives us also the function, right? So that's going to be my choice of function and U, and what I'm going to have is that X is statistically independent of S, and X is going to be a Gaussian random variable with zero mean and power, of course, P. Oh, okay, I forgot to add this. We need a power constraint. So here I haven't, actually it's a, so I haven't done this. Formally I should do this result with the power constraint, I guess, by invoking the Gaussian example, but I guess I already mentioned what the result is. It's the same maximization. It's just constrained so that the expected cost, so here's the cost function of, I'll say something about that in a moment, but in any case, we're just choosing this with the power constraint. So everything will go everything goes through with a constraint as well. I hope you believe me. So anyway, even if you don't, tough luck, right? So X is independent of S. Is that what you'd expect? I wouldn't, right? I would guess here, well, if we use that intuition we had before, I would guess we would choose X to ride the interference, right? It's a little weird. And every time I look at this, I tend to get confused, and I think it is confusing. Why would I choose the N-channel input to be independent of the interference? That sounds like a really bad strategy, right? But it turns out, of course, that here x is equal to u minus alpha s, so u and s are correlated, right? U and s are correlated, and u is what carries the information directly, not x. But even that intuition, I mean, it's sort of weird to get all this stuff right in your head, like what does what mean. It'll turn out this is the right choice, though, and it'll turn out that the right choice for alpha is going to be a choice that is based on minimum mean squared error estimation, which I'm not going to, derive here why we make this. I could. I'll explain why we make it, but I won't derive it. Okay? But you'll see why. But this is now going to be my explicit choice of function. So again, as an example, suppose the interference is really tiny, then well, the natural thing, natural thing to do at the transmitter, if you know the interference, is to subtract it off, right? Why wouldn't I subtract off the interference? So why wouldn't I choose x to be like a u minus, alpha s, which is what I'm doing, right? So maybe we're subtracting off part of the interference, but if s is really super strong, then I can't subtract it all off because it's too strong, right? So, what do I do? Well, it turns out that this is the right choice. So there's a lot of ways we should try to understand this later intuitively, why you would do this. Okay, and it's not obvious. These things aren't obvious. And when you try to implement it, it gets even less obvious. And maybe I can say a few words about this at the end. Anyway, this turns out to be the right choice. Let's prove that. So let's start with this. Let's compute this here. Right? We need to compute this. So let's start with the differential entropy of u given y. Well, this is h of x plus alpha s given x plus s plus z. Right? And so I can subtract off here any linear, any weighted version of this. So what I'll do is I'll subtract off the alpha times x plus s plus z. Okay, and then the alpha s's cancel, so I'll get h of 1 minus alpha x. The alpha s's cancel minus alpha z. Right? Is that okay? All those steps? Now I claim these two are statistically independent. How can I prove that? Well, what I have to prove is S is not Gaussian, so I have a problem. Okay, what do I do? Right, so what I want to prove is the following. I want to prove x plus z is independent of this, and s is independent of everything here, because the noise, x is independent of s, remember? So x and z are jointly independent of s, so x plus z is independent of x, and here we have only linear combinations of x and z, so certainly s is independent of everything else here. So as long as I get x plus z is independent of what's in here, I'm fine. Okay, so let's see if we can prove that x plus z is statistically independent of what's in front here. And to show that, because these are all Gaussian, x plus x is Gaussian, z is Gaussian, so x plus z is Gaussian, this is also Gaussian, we just need to show they're uncorrelated. So let's take a look at that and check if they're uncorrelated, and you'll see that's why I made this choice, is to make them uncorrelated. So, I can quickly check that. So the expected value of 1 minus alpha, well, alpha is p over p plus n, so it's going to be, well, let's just do 1 minus alpha. 1 minus alpha x minus alpha z times x plus z, what is that? That's equal to 1 minus alpha, the expected value of x squared, but that's p, minus alpha, x and z are uncorrelated, that's 0, so we get m. And you can quickly check that this is nothing than n over p plus n times p minus p over p plus n times n, so this is just 0. Okay, so they are uncorrelated, and because of that, this is independent of x plus c, and s is independent of everything, so they're independent, so I can just drop this, right? And I can stuff back in anything that's independent of this, which I'll just do, it's x plus z. So I'll just stuff back in something that was independent x plus z. Right? All with equality. So I took everything out because I just want to take the s out, you know, so I get this back. And now I can just, again, add x plus alpha. I can multiply this by alpha and add it back, and I'll just get h of x plus z. So that's nice. I got rid of the interference completely in this expression. Okay, got rid of it completely. So now there's one more step. We had h of y given u minus h of u given s. Right, so h of u given s is going to be easier because u is up there. Right, which is equal to h of x given s, but x and s are independent, so it's nothing but h of x. Right. So what I'm getting now is right, so the mutual information is that minus that, right? That was the rate I can achieve, so this implies that y minus ius is just h of u given s minus h of u given y is just going to be ixy. So no interference, and since everything is Gaussian, this is just 1/2 log of 1 plus p over n. Okay, that's the remarkable dirty paper coding result. Namely, that if the noise is Gaussian and S is anything, any interference, really huge, it could be huge interference, huge, and the receiver doesn't know what it is. Only the transmitter knows what it is, and yet you can communicate at the same rate as if interference wasn't there. And that's a very surprising result. Again, this was first derived by Max Costa in '85 with a footnote. Thank you to my supervisor, Tom Cover, for pointing out that this could be true. Something like that. And I'm pretty sure because he knew the Weiner-Ziv results, that is natural. I think if you see the duality and you realize that, I think it's natural to guess that, but you still have to check, of course. So, very nice result. Practically, how do you do this? Well, let's take a look at this random variable here. So remember, u was our code book. So if we're thinking of doing like modulation, you'd probably want to choose u to be like 16 QAM, 64 QAM, or something like that. Alpha, well, suppose the signal-to-noise ratio is reasonably large, then alpha is just 1. And note what we're then transmitting. We're transmitting x is u minus alpha s, and alpha might be close to 1, so x is u minus s. So we'll have to choose really huge u powers, right? And anyway, so this is a huge number, s is a huge number, it might be something with huge variations, right? So u has to be something with huge variations. That means we have to do modulation sets on something with huge variations. That doesn't sound very practical, does it? It doesn't sound that way. So is there a way of doing something more smarter? It turns out the answer is yes, but this is not obvious. It turns out that the right way to deal with these, or one way, which seems to be, in my opinion, the most practical way of dealing with this problem, is to do something called, well, it's very closely related to Tomlinson-Hiroshima precoding. So if you know Tomlinson-Hiroshima precoding, what you do is you have a modulo operation. So if we could somehow modulo out the S, and that's what you do in the most practical method, you take a modulo, then you can keep the dynamic range of the U's in reasonable form. I mean, the dynamic range of the X's have to be limited to the power constraint, but we want to also keep the dynamic range of the U's within some limitation, and that is possible to do if you do, we could even do Tomlinson-Hiroshima precoding or modulo operation in one dimension, and it'll already work reasonably well for high SNR. But to really get the full power out, we'd have to do modulo operations over larger sets. This is where lattices come in and stuff like that. But those are hard to implement again, right? So there's still work to be done on how to build this practically. That's my main point. There's still no really, I would say, good approach to really get to Shannon capacity for this problem, Shannon to this rate. There's some good methods that get close, like again, Tomlinson Hiroshima, pre-coding. The first paper on this topic with coding was due to Uri Eretz and Stefan ten Brink back around 2003. Very nice paper. They applied this modulo idea. They did first a simple quantization, and then modulo operation. Here you also do modulo operation. And they got rates reasonably close to capacity for high SNR, but still pretty far away at low SNR. So there have been improvements. People have started, around 2010 or 11 or 12, there was a paper that just chose a better vector quantizer, something like a trellis-coded vector quantizer with like 1,000 states, and then they got even closer to capacity. But it was more taking a hammer to the big sledgehammer to the problem to try to improve things. It still is far away at low SNR. So I think it's still an interesting problem. Even this model is still interesting. Never mind, like fading stuff is interesting too, and all that stuff. Not a lot of work has been done on this yet, so in terms of coding. Any questions? Yeah.
So here we are taking the constant summation of x square.
Yeah.
This thing, what if each symbol we will put?
Yeah. So, right.
The total one.
Right. So if we do this instead, then the answer will be the same. But but notice that this is only an average constraint. If you put an amplitude constraint on it, well, then it also gets trickier. I don't think there won't be a closed form expression anymore, and you won't be able to remove the interference completely anymore. I'm quite sure about that. But it's an interesting question to ask. I don't think anyone has ever looked at this problem with amplitude constraints. I don't think anyone's. I don't know of any paper that's looked at that. What can you do now with interference? It's possible you still can. Well, actually, I guess the modulo operation already tells you can have amplitude constraints. But the thing is, you might have to get capacity, you might have to do this modulo operation over larger and larger intervals, and then you won't be able to get rid of interference again. I'm not sure, but I suspect that's going to happen. But there's been very little work on that problem. It's a nice salamander walking up behind there. So I don't know if it's a salamander or just a Eidex, how you say in German. Anyway, good. Any other questions? Okay, so if not, I will just do the converse. That's the last thing to do. It's not going to take that long. It's just a few lines. The hard part is organizing it properly as usual. But it's going to be a little different than the Weiner's if problem. Okay, so let's do the converse. Again, for the converse, we have to look at the general, any kind of encoder and decoder. Okay, so for reliable communications, we need to have that the rate is less than the end-to-end mutual information. Okay, now most people write here some fuzzy stuff yet due to Fano's inequality, but that's why I like to say for reliable communication, the error probably goes to 0, then I can just ignore that, right? And that kind of, I think, cleans up the... But some people don't like this, because it's strictly speaking not right, but I'm qualifying it, right? So I'm happy with it, so... But some other people don't like this. Fine. So, but the point is that for reliable, to send reliably by meaning, I mean arbitrarily small positive error probability, we need to satisfy this constraint. Now, we do the usual steps first. We're going to use the data processing inequality, right? This is less than I of W yn, right, by data processing inequality, right? You know that. Mutual information between here and here is always less than between here and here, right? Or then here and here, or there and here and here, but we'll keep the W for the moment. Okay, so here comes the first trick, and this is my favorite way of doing this. Unfortunately, I haven't convinced other people that this is a good way of doing it. I'm going to use something called a telescoping identity, so let's do this here. And I claim that this, I'll just write it out and then we'll check. I claim that this is the same equality as this. And then we'll check this. Okay, so it looks a little weird, right? I'm splitting a single term mutual information up into a sum of terms, but let's take a look at here. Here, notice the index goes from I plus 1 to n, and this is I, and this is just one index step down, I minus 1. So you can see the neighboring terms cancel, right? It's the same as doing an integration. You take this, minus this, plus this, minus this, plus this, minus this, plus this, and so on, then you just get the n terms. Right, so here only the n terms will be important. Let's look at I equals 1 and look at I equals n. So let's see here. For the very first I equals 1 term, I only have to take, let's see here, this one. But if I equals 1, this here is nothing. It's a constant, so I get 0. So one n term is 0. Let's look at the end term at n. That's this one here. Well, there I get Sn plus 1 to n is nothing, and I get just Yn. So I'll get this term, right? So this is sometimes, called a telescoping sum, but it's the same. I like this version of the bound. In all other textbooks, you'll see something called Cheezar's sum identity used, and you see it used twice, I think, or once. Maybe it's only once. I think it's used twice. It is twice, isn't it? Or is it once? I forget. Anyway, I like this because it reminds me of integration. Okay, there's a kind of integration going on. Okay, now with this, I can do just chain rule to get a simpler expression. I mean, using Cheezar's sum inequality, you effectively do the same thing just with 2 or 3 more steps, right? But it's this otherwise very similar. This is just a little bit simpler. So, what I want to do is I want to write this out. I want to get 2 canceling terms, so I'll write this as I of W S I plus 1 to n yi minus 1 plus I of W S I plus 1 to n yi given yi minus 1, right? So I just wrote out, used chain rule on this, right? That's all. I just used chain rule. I took one piece out here, right? And I'll do the same thing here. Minus I of W Si plus 1 to n yi minus 1. So these 2 terms will cancel. Plus I of Si yn I minus 1 given W Si plus 1 to the n. Right? It's just the same thing. So cancel, cancel. And now I just write out these expressions. So, h of yi given yi minus 1. That's this one, yi minus 1, minus h of yi given w yi minus 1 si plus 1n. And then minus h of si given w si plus 1 to the n. Now, as long as si and w si plus 1, notice that the s here in the model is independent of w, and we're taking here that the s's are iid, and then of course the h of si given this is just h of si. Minus h of si, given also this funky looking term, yi minus 1, si plus 1 to the n. Right? And this is what I'm going to call my ui. So this is what I will define to be ui. Okay, and now just putting this together. We're almost there, although a few more steps. So what we have now is NR. For reliable communications, we have this is less than or equal to summation from I equals 1 to n. Of course, this is less than h of yi. So here I'm just going to get I of ui minus I of ui si. Which looks exactly like we need it to look, right? This thing here is less than or equal to n times the maximum over all I of ui yi minus I of ui si. And as long as I get the Markov chain that I need, namely, I need a Markov chain u, x, s, y, I could write here that this is less than or equal to n r Gelfand-Pinsker, right? So all I have to do is check whether that Markov chain still holds or not. So does it hold if I have this ui? Well, yes, because yi is just a noisy function of, like inside here you won't see, there's no xi or si. So indeed, for this choice of ui, you can convince yourself I do get that Markov chain, so that means I can write this. Because this is just the maximum over all possible such differences in mutual information with that Markov chain, right? Because that's how I defined this, right? Remember, this here is the max over all p u given s and functions f. Oh, I don't have the function yet. So there's one extra thing, actually. We still have to prove. So if I define this to be xus, so this is now with what's called randomized encoding. If I defined the Gelfand-Pinsker rate to be this, then I could claim this was true. But remember, I defined the Gelfand-Pinsker rate to that x is a function of u and s. Sorry? Oh, s. Thank you. Yeah. Right. So if I define this to be this with the Markov chain u, x, s, y, then I could write this inequality. Remember, I wrote the inequality that x was a function of u and s. So I still have to prove that the optimal choice in here is to choose x to be a function of u and s. And I'm not going to do that, but what you can show is that the Gelfand-Pinsker rate is convex in px given us. And since we're trying to maximize a convex function over the distributions, we'll get the maximum at one of the endpoints. And the endpoints of probability distributions are the functions. Okay, so I won't prove that, but you can show that this object in here is convex function of px given us. Given everything else is fixed, you can show it's convex, and that tells you that you should choose this to be a function. Okay, so, and then I can claim this is the Gelfand-Pinsker rate with pu given s and this function. Right, that's what lets me simplify it down to a function. Anyway, it's very fast, I know, but so this is how you prove the converse. So the hardest part, well, there were some tricky parts. The telescoping, some certainly isn't obvious. In almost all books, as I mentioned, and papers, they use Chizar sum identity. Chizar sum identity is really easy to prove with telescoping. I think it's the easiest way to understand it. These steps are pretty straightforward, and I guess there's still the tricky step in showing convexity to get the functional form. But if you don't like the functional form, you could just do randomized encoding too. Then we would have px. You get the same answer. So it's just a simplification of the region. Anyway, it's a remarkable form for the region. Building codes for this is really interesting. Same kind of codes as for Wiener-Ziv coding, right? Similar codes. We need compression step followed by decoding for both problems. And there's a lot of, I think, still potential in designing coding schemes with this shape for base station communication. Hasn't been, there's always some work kind of going along on it. I know that Nokia Bell Labs has one group working on it right now. They recently put something on archive. So it's clear, like the corporations are also, the research groups are still interested in seeing whether they can develop something here. So it is happening. It's not as if people have lost interest in this. But there's not many people working on it. So. Good. Any questions about this? So translating all this stuff into real codes is really interesting problem. I mean, that's not obvious, and it's a real challenge to do that. But the information theory tells you can accomplish something. We have converses to show you can't do better, so it's fascinating to try to figure out a way of actually building this stuff. Polar codes are really nice because they can do compression as well as coding, and they're nested, so there's a natural form there. Unfortunately, polar codes are pretty bad for reasonable block lengths unless you include list decoding and a CRC as a concatenation. So that's the work by Talvardi, which last year got a paper prize deservedly for this work. It's a very simple trick to improve polar codes, but extremely effective. Whether that works well with a vector quantization and channel coding kind of structure with nesting, I don't know, right? That's an interesting problem to think about because you need to do that if you really want to make them practical and competitive for shorter length. Another approach is to use convolutional codes. They're really good at quantization because you can have a maximum likelihood decoder, and they're good for coding for short lengths, which is really interesting. Interesting problem, how to design large constraint length convolutional codes that work well for both in a nested fashion. I think that's a really good choice. Otherwise, LDPC codes have the problem that they don't quantize so well, right? So they're not such a great choice, or I'm not sure if they're a good choice. They're not usually very good for unless you go to really long block lengths, then they can start doing something. Spatially coupling, for example, that'll work too. Spatial coupling work, but those block lengths are so crazy long. The only thing I think they're useful for is fiber optic communication, where you do have block lengths of 1 million or so on. Right, it's the only example I can think of. So anyway, that is very interesting, and also for companies, I think that's the interesting thing to do, is to try to convert these problems to practice with real codes and real coding. Fine, so if you have no questions, then we'll stop for today. And work on the broadcast channel tomorrow.